All right, welcome back. Today we're talking about planar rigid body kinematics. Planar bodies are two-dimensional bodies that need to be described with x and y axes, so you're really dealing with a planar area. In addition, we are constraining the problem by only looking at rigid bodies. So these are not bodies that are deformable, because mathematically describing deformation can be very challenging. So we're basically looking at kinematics of planar bodies that are rigid only. So suppose you have a body that's shown here in the green. It's described with x and y axes. You have 2 points on it, and the body is following some sort of path. Because the body is, in this case, rotating and translating at the same time, any 2 points on this body will have or will be described with two different paths. So we have points A and B, each having their own paths. So we also have thetas, which describe the angular trajectory, the rotations. We have omega, which is our angular velocity. And we have alpha, which is our angular acceleration. So what I want to do now is I want to describe the position of point B relative to point A, because this is really useful in tackling a whole class of problems. So what I start off with is this positional vector RBA. And this is a vector, so what I'll do is I'll put a bar over it, on top of it. And this is really describing position of B relative to position of A. And of course, because it's a positional vector, you will have x and y components. So the way we really describe such a vector is some constant I plus another constant j. And these usually has units of meters or feet or whatever it is that you'd like to work with. Now, once we have this, we could also talk about the relative velocity, right? So let's talk about this velocity vector that is describing the velocity of B relative to A. So looking at this shape that I have an angular velocity omega, so I can certainly utilize that. So the whole thing is rotating. So I have omega, we can describe it as a vector. And then this omega has to be multiplied with the positional vector to give me my translational velocity vector. So we have a cross product, and we have our BA. So this is what this is really doing is it's taking your body that's rotating, and it's computing this velocity vector that is at 90 degrees with the rotation. And by the way, we describe rotation here as a vector because it's sort of like a vector that's coming out of the page. So if you're looking directly at the screen, the rotational vector is coming right out. So it'd be sort of in this direction out of the page. And a positive rotational vector for this chapter is always counterclockwise. Okay, so we have the relative velocity vector in vector format. Something else that also happens is any body that is rotating, it will have a translational acceleration and a rotation and a normal acceleration. This was something we figured out from prior chapters. So if you can imagine, we have a bar, it's rotating around a pin. It will have a translational acceleration term. We call this AT, and it will have a rotational one, which is sort of due to the centripetal effects. So now we want to describe those as well. So let's see, we call this A, BA, normal, and we give it a vector bar. This is described via omega hat cross product VB hat. So that's how we can describe it. We could also plug in the velocity vector here to get something that's a little bit more expanded. So we have this cross product RBA. So what you're seeing here is that your normal acceleration, anytime you have a planar body, it's rotating, the normal acceleration is dependent on the length of the body. So that's sort of described by R, and it's described by the angular velocity. So normal accelerations don't depend on rotational acceleration. They only depend on your rotational velocity. So that's an important concept to note. On the other hand, we have translational acceleration, and this here is strictly dependent on alpha, which is your angular acceleration. So you have alpha bar cross product RBA. So this was all done in vector format. Now what we could do is we could describe this whole thing in scalar format as well. So in scalar format, we have to do a little bit of geometric analysis. So if we're looking at the velocity, and this is velocity of B relative to A, we can look at the magnitude of omega RBA. So we're looking at this magnitude. Now, because omega is having a vector that's coming out of the page, so it's 90 degrees coming out of the page, and RBA is going on the page, there is a 90-degree angle that exists between them. And if you guys recall from the definitions of cross product, we have omega dot product RBA sine beta, and beta would be some sort of angle between this k vector that's describing omega. So omega is going around, the k vector is coming out of the page, and this here is the r vector, and it's described by the I unit vector, or the I and j unit vectors. So this is here screen that you're looking at, and this here is the vector that's coming out of the page. So these are always at 90 degrees. So the angle between them, beta, is equal to 90 degrees. So here, if we have sine of 90, then this whole thing becomes 1, and you end up with RBA dot product omega. All right, so now we could do acceleration. We can look at the normal acceleration in scalar format, and it's really the same process. We have omega cross product so we have this. Again, using that same cross product rule, we have omega sine of 90 degrees. And this gives us omega, or I like to, let's keep omega first, omega VBA. So that's what we end up with. We can plug in the scalar we found out earlier, which gives us omega squared RBA. Scroll down just a little bit more. Now we can look at the tangential components. So we're looking at this. We're looking at the magnitude alpha cross product RBA. And this gives us alpha R sine of 90 degrees as well. So we have R alpha. So now it's a good time to look at an example. And within this example, we want to demonstrate one of the methods that's very common for analyzing planar kinematics. This method is called the method of relative motion. So we're looking at the method of relative motion, and basically this process involves looking at a body that has multiple components and analyzing the relative motions of the ends of the components and adding them together. And you will see in a second what this means. So what I'll do is I'll draw a schematic. Okay, so we have this body that has two arms and a slider. The two arms are arms AB, BC, and the slider is C. So the slider is pretty much going back and forth in this direction or in these directions based on the angular velocities and positions of the other arms. So what the problem has specified for us is an initial constant angular acceleration that exists. So we have omega AB is equal to 4 radians per second. And what you need to find out is the velocity of the slider. Okay, so now what we could do is we could utilize the relationships we identified earlier. So what I'm talking about is basically all these equations here, these three, and these three, which are pretty much the same things, but it's useful to utilize all of them. Okay, so we want to find velocity at C. So what I can do now is I want to start off from the fixed position, which is down at position A. So at position A, I have a pin. So it's kind of fixed, and it's convenient to work off of there because I know A is not moving. If I know A is not moving, then I can describe the position of B relative to A. And once I know how B is moving, then I can describe how C is moving relative to B. And that's really the basis for the method of relative motion. You take something that's sophisticated, you break it down into chunks, and you work with it that way. So let's start by looking at the link AB, or the arm AB. And here we have VB is equal to omega AB, which is given, dot product R BA. So that's what we're trying to compute. And of course, the 4 radians per second is given to us. And RBA here is roughly 15 inches in scalar format. We could also describe it in a vector format, so that could all be done. And here we have 60 inch per second. And just to show you what we computed, we have our first arm, AB. A is pinned. It's being rotated in a clockwise direction. That is at 4 radians per second. And velocity B here is at 90 degrees to this arm. It's sort of like a tangent around this circle that B is rotating around. And this is velocity B. And that's really how you compute that value. Okay, so now we have velocity B. We want to start looking at link BC. So that now we want to look at this. So what I want to do to begin with is I want to take my velocity B and write it in vector format. So we have velocity B. In vector format, it will be VB bar. Looking at my velocity B, it's going in the right direction and it's going slightly downwards. So I should have a vector that is positive in the I direction. So that's the I direction. And it will be negative in the J direction. So let's see. We have 60 cosine 30, right? If this angle is 60 degrees, this is 30, and this is 32. So that's where the cosine 30 is coming from. So we have this going on. We put a unit vector I in front of it, and then we have minus 60 sine 30 j. Now, we want to look in more detail at link BC. So if this is my link, velocity B is already computed. It's in this direction. And I know velocity C is going in this direction. Now, when arm AB rotates, arm BC is expected to rotate as well with some sort of constant angular velocity. So I suspect there will also be an omega going in this direction, and we call this omega BC. And if we scroll up just a little bit, I can now use some of the relationships we had before. So I can use this relative velocity term and add it to my absolute velocity term. And what I mean by absolute is velocity B here is absolute because it's measured relative to a fixed point. So it's really a constant value. It's not relative to anything. So here velocity C is equal to velocity B, that was the absolute value, plus the relative term, which is velocity C to B, right? Velocity at C relative to velocity at B, and we could expand this by saying this here is omega BC cross product RCB. So this is all written in vector format. RCB is positional vector from B to C, or C relative to B. So here we are going first to the left and then we're going up. So we have a negative and then a positive. So what is it? If this arm is 20 inches, we have minus 20 sine of 30, the angle is given to us in the problem. And then we have plus 20 cosine of 30j. And this whole thing is written in inches. It's useful to have the units, and in fact, I need to put the units down here too. So these are my units. Okay, so going back to this important equation, we could utilize it. We could say VC is only going in the horizontal direction. So in vector format, it's VCI. And this is equal to 51.96 I minus 30j. And that's just velocity B. So if we simplify this, we get something that looks like this down here. Plus omega BC K. So omega BC is always rotating about this vector that's coming out of the page. So that's the K vector. Cross product minus 10I plus 17.32J. And that's really an expansion of this. And of course, cross products need to be done using this cross product matrix. They are a little different than the dot products we've done in the past. So we have 0, 0, omega BC, and we have minus 10, 17.32, 0. And here, when we use this cross product matrix, we get something that looks like this. Might be a good idea to review matrix algebra, at least when it comes to the different multiplications that exist. So I just want to make sure I wrote everything down correctly, and I believe I did. Okay, so we're good. We calculated the cross product, so we already know what the expansion here looks like. And so once we simplify, we have VCI equals 51.96I. This could be further simplified as And of course, the left side has to equal to the right side. The left side has no j component. There's only an I component. So making the I components equal to each other, we have VC is equal to and for the j component, we have 0 is equal to minus 30 minus 10 omega BC. So the equation on the right-hand side gives us omega BC is equal to minus 3 radians per second. And the equation on the left gives us VC is equal to 8.66 feet per second. And VC is going to the right-hand side based on the original angular velocity, and omega BC is here is negative. So, of course, the actual direction of the rotation had to be the opposite of what we originally intended. So we can always go back and fix that. All right, so this is one of the methods that we usually deploy, is the method of relative motion. There is another method by the method of instantaneous center. So this method really stems from the observation that we have that velocities are always orthogonal to their positional vectors. So whenever you have an arm that's rotating, and this arm is sort of pinned around a position, your velocity is always at 90 degrees to the arm. And so whenever we look at a body that has multiple arms, multiple components, the velocity components go through a center of rotation, and we call that the instantaneous center. So let me just make a schematic for you so you can really see what I mean. Okay, so here what I've done is I've isolated arm BC, and I've drawn the vectors that are on either end of this arm. So we have vectors VB and VC. We kind of know in which direction either of them go. Velocity B is computed from omega AB, and velocity C is sort of bound by that slider. So we have a good sense of which way the directions are. Now, what I can do is I can draw an arm, I can draw a line going from the velocity vectors, and more specifically orthogonal to these velocity vectors, and I can have an arm from both of these velocity vectors to see where they coincide. So I have B and C. I take orthogonal components from either of them, and where they cross becomes my instantaneous center of rotation. So your arm BC is always rotating about IC. So that's really an interesting phenomena. So it's important to note here that we already know what a VB is. It's basically 4 times 15. So we know this is 60 inches per second. What I can do is I can use the law of sines. If you don't remember, the law of sines was if you have the interior angles alpha and beta, and I know the outside perimeter of the triangle, so if I know what B is and I know what A is, then I can relate those relationships as A over sine alpha is equal to B over sine beta. So that's something that I could utilize. So here what I can do is I can say, scroll down just a little bit, I can say RCIC, so position of C relative to IC, divided by sine of an angle. What is the sine of this angle? This angle is 60 degrees. This is something we knew from earlier. We knew this angle was 30 degrees, so this must be 60 degrees too. So this interior angle is 120. 120. This can be set as equal to 20, which is this arm's length, that's 20 inches, divided by, and this angle here is 30. It basically has to do with the angle of this arm that we originally had, because the vertical component was always 30. So we have sine 30. And using the law of sines, RCIC is computed as 34.64 inches. I also need to know what RBIC is. So again, using this method of the law of sines. And lastly, RBIC is equal to 20 inches. Okay, so at this point, I already know what omega AB is. I know what velocity, so I know this. I know what velocity B is. What I need to find out in this case is what omega BC is. So that's an unknown, and I need to know what velocity C is. So I'm basically doing the same problem that we did for the relative motion method. This time we're using the instantaneous center method. So here what I could do is I could say, I already know velocity B can be described as omega BC times RBIC. That's just a fundamental relationship. So if I know omega BC, which is shown right here, and if I know RBIC, then I can find VB. Except the problem is a little bit inverted. In this case, we know VB, we know RBIC, but we don't know omega BC. So what I can do is I can rearrange this equation so that the unknowns are a little different. So I get a relationship that looks like this. And so plugging the answers in, 60 inches per second, 20 inches, I will get omega BC is equal to 3 radians per second. And lastly, I can compute velocity C. So this here is just omega BC dot product RCIC. So again, we're using the instantaneous center to compute the velocities, and we have 34.64. That's my positional vector, and basically what I'm doing is I'm multiplying that by 3 radians per second. And my velocity at C is equal to 103.9 inches per second. Now, I do want to add one more piece of information, and it's basically an elaboration on the method of relative motion. Whenever you're looking at relative motion, but instead of velocity, you're looking at acceleration, you can go through the same process that we did, except for the acceleration vectors, position B can be described as position A plus the normal components of the acceleration. So you have omega cross product, omega RBA. So that's the normal component. And we have the tangential component. So we have alpha cross product RBA. So that's really how acceleration for the relative motion can be computed. It's a little different. Alrighty. Well, I hope this was helpful, and I'll see you next time.